तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Good morning. This lecture we change gears and we leave behind both electrostatics and magnetostatics, and we are going to discuss a completely new phenomenon. It is a phenomenon that Maxwell introduced in the second half of the 19th century, and it is a extremely important idea. It joined together different fields of physics and made them into one single subject. To bring that topic into focus, I am going to review a little bit. First of all, if you remember back, we said that the magnetic field was got from a force equation observed, mind you, which said that is equal to I dl1 cross I dl2 cross r12 over r12 cubed, and there is a mu naught over 4 pi, and this bracket was identified just like we identified the corresponding bracket equation in electrostatics. We identified this with the magnetic field, and so we defined something called the magnetic field, which was mu naught over 4 pi, the constant came in, integral over all space, this I dl times dA became a j cross r12 over r12 cubed dV. So, just to remind you, the j dV is really I dl, which is j, the vector under dl I am associating with j. So, dl times dA, because current is current density times area, and this dl dA is my dV. So, that is where j dV came from, and so I defined a magnetic field integrated over all space, which was the current density cross r over r cubed. So, magnetic field is proportional to 1 over r square. As you go far away from your currents, magnetic field drops as 1 over r square. So, it also has an inverse square law. Some few lectures later, we looked at the problem of the field due to a loop. The loop is carrying a current I, and it has an area dA, and because of the right hand rule, the area is given a direction. So, I will call it ds. So, if I have a loop of current and if it points in the direction ds, I defined a quantity called the magnetic moment m, which was I ds, and in terms of this m, you could find out what the magnetic field was. First of all, we had also found out that B is equal to curl of something, and that something is called the vector potential. in terms of this vector potential, I could work out B. If I knew A, I just take the curl and I get B. And for this small loop, if you work out what the vector potential is, you find that is equal to mu naught over 4 pi m cross r over r cubed. Now, this is surprising, or it is surprising if you do not think about it, because here magnetic field is going like 1 over r squared, here vector potential itself is going like 1 over r squared. If you take this vector potential and find the magnetic field due to it, you get B is equal to mu naught over 4 pi times the magnitude of m times twice cos theta along r plus sin theta along theta divided by r cubed. Now, just to put things into context, let us look at what electrostatics has to say. If you have a charge plus q and a charge minus q which are a distance d apart, I can define something called the electric dipole P, which is equal to q times d, that is the charge times the distance between them. The corresponding analogy is I have defined a magnetic moment which is the current times the area. Both of these are vectors because they have a direction. Now, in terms of this P, if you work out what the potential is P dot, well, there is a multiplying factor, 1 over 4 pi epsilon naught P dot r 12 divided by r 12 cubed. So, the potential, unlike for a charge, the potential due to a dipole is proportional to 1 over square of the distance. And if you work out the electric field, E is equal to 1 over 4 pi epsilon naught times the magnitude of P times twice cos theta in the r direction plus sin theta in the theta direction divided by r cubed. Now, I am sure you can see the symmetry between these two equations. B is some multiplying factor times the magnetic moment times a vector function. E is another normalization constant times the dipole moment times the same vector factor. So, both E and B have the same form when you consider that electric field is due to a dipole and magnetic field is due to a ring, which is why magnetic rings, tiny rings of current, are considered to be magnetic dipoles. Okay. Now, using this concept of a magnetic dipole, I further argued, this is only an argument, the actual proof is given in your textbook, that you can construct any general current density by just stacking all these little rings. And so, if we know the properties of one ring, we sort of know the property of magnetic field in general. And I showed for you that for a current ring, curl of B is 0, or actually curl of B is 0 if R is not equal to 0. If R is equal to 0, curl of B is not 0, and we looked at that problem and we finally concluded that curl of B in general was equal to mu naught G. Now, we could have done the same argument, we could have taken the divergence of E we would have found that the divergence was 0 except at r equals 0, and at r equals 0 we know how to calculate the divergence, and so we could have got a divergence statement for electric field as well. Now, the importance of all this is the following. Supposing I go back to this original equation, this is where everything came from, even this calculation came from this equation, and let me consider, let us say that we have x, y, z, and that I take a small piece of current I naught for a distance dl along z. Biot-Savart tells us that such a piece of current creates a magnetic field far away. This is r, then the magnetic field at this point B of r, I should say dB of r, is equal to mu naught over 4 pi times this current element I naught dl along z cross r divided by r cubed. This is just the fundamental starting equation we had. Now, what happens if I have only this piece of current and I take its curl? Now, I know that curl of H is equal to J, or let me use curl of B is equal to mu naught J. So, since my only current is here, curl of B should be 0 everywhere. So, let me try taking the curl of this quantity. So, the curl of B is going to be unit vector along x, unit vector along y, unit vector along z, derivative along x, derivative along y, derivative along z. The x component of this vector, let me pull the constant parts out, mu naught over 4 pi I naught dl. The x component of this vector is z cross minus y. So, it is going to be minus y over r cubed. The y component is going to be z cross x component. So, it is x over r cubed, and the z component is going to be 0, z cross the z component is going to be 0. So, that is what the curl is going to be. So, I can evaluate it, and let me write it out. It is going to be equal to mu naught over 4 pi I naught dl times the x component is x hat del del y of 0 minus del del z of this quantity. So, minus x hat del del z of x over r cubed. The y hat component plus y hat is going to be del del z of this quantity minus del del x of 0. So, it is going to be del del z of minus y over r cubed, and then the z component is going to be these two terms, which is del del x of x over r cubed minus del del y of minus y over r cubed. So, it is a vector. Now, if this is to be 0, then each of these components must be 0 except at x equals y equals z equals 0, that is the origin, because that is the only place where we have current. But if I take the z derivative of this term, for instance, what is it equal to? Del del z of x over r cubed is equal to del x del z is 0. So, x is a constant as far as this partial derivative is concerned. So, it becomes minus 3 over r to the power of 4. I take the derivative with respect to r, therefore minus 3 over r to the power of 4 del r del z. But del r del z is clearly not 0. If I move in the z direction, r is going to change. Therefore, this quantity is certainly not 0. It can be 0 if x is 0, but it does not have to be. Whereas, here we are claiming that it is 0 no matter what. So, this is not equal to 0. Neither is this for the same reason. And you can work this out and you find that this is not 0 either. So, we have a problem. The problem we have is that we started with Biot-Savart law, we applied an equation that we know should give us 0, and the answer is definitely not 0. So, we have a problem clearly. Either this definition is wrong or this equation is wrong. One of the two must be the case. Now, in the case of the magnetic loop, we did not have this problem. When we wrote down the magnetic field for a loop, we found that magnetic field B was mu naught over 4 pi, magnitude of the magnetic moment times twice cos theta r hat plus sin theta theta hat divided by r cubed. Now, this does not say that we do not have a curl. However, we know something else. We know that for a dipole, the electric field is equal to 1 over 4 pi epsilon naught p times the same quantity, twice cos theta r hat plus sin theta theta hat divided by r cubed. And we know something else. We know that however we got this, it came out of the gradient operator acting on potential. So, if we take the curl of B, apart from a few constants, it is like taking the curl of E, and taking the curl of E means taking the curl of a gradient, and we know that curl of gradient of anything is identically 0. So, for the loop, we can show that this piece is the gradient of something, and because it is the gradient of something, the curl of B is 0, which means Ampere's law is satisfied. Whereas, for Biot-Savart law, Ampere's law is not satisfied. Something is going on. We have a law that we have satisfied ourselves about. It predicts everything that we know about in magnetics, and yet it is failing this basic law the moment we use the basic building block of magnetic field. As I said, either this is wrong or this is wrong. Now, we will come to the how to change this law when we start looking at it slightly differently. But this is the current message, namely, if I start with Biot-Savart law, I can work out an expression for curl of B, and that expression is definitely not 0. There is no way it can be 0 everywhere, and yet we have a law saying it should be 0. if you have a current I naught that is steadily going from minus dl over 2 to plus dl over 2 in the z direction, it is like I have a discharging capacitor. Current is steadily flowing, so negative charge is building up here and positive charge is building up there. How much positive charge? If I call this Q, Q is equal to I naught times T, because I naught coulombs per second are flowing into this point. So, the charge must be I naught times T, assuming that the charge is 0 at t equals 0. So, I have a dipole. My dipole P is equal to the charge I naught T times the distance between the charges, which is dl in the z direction. There is one way to make sense of this situation. Supposing you take curl of H is equal to J. Now, I can take the divergence of this equation. This is nothing but Ampere's law. So, if I take divergence of this equation, that is what it gives me. But divergence of a curl, as we saw last class, and in fact several classes we have seen this, is equal to 0. But divergence of J, we know, is equal to minus del del t of the charge density. The reason is, if you have a region in which there is current flowing out, then it must be that the charge contained is reducing. So, divergence J is definitely equal to rate minus the time rate of change of charge density. So, in other words, this equation is only true for statics. It is only true when charge density is constant, and this particular case is a case where charge density is not constant. It is continuously building up because of this time derivative of this time dependence. So, what would you require to make this equation correct? You would require another term. You would really want plus, well, let me use another color chalk. I want a term that goes like plus del rho del t. If I had a plus del rho del t, then I would have 0 is equal to minus del rho del t plus del rho del t, and then that would be 0 equals 0. So, I would be happy. The question is, how do I get this plus del rho del t? Well, I have another equation. I know that Gauss's law has told me divergence D is equal to rho. So, instead of saying plus del rho del t, I can say plus del del t of divergence of D. Why does this matter? It matters because I have taken divergence of this whole equation. So, I can pull the divergence out, and I can write this equation as divergence of, and I am going to do this in a way that is not correct, but it makes it clear, curl of H equals J plus del D del T. Of course, I should not do this. I should in fact take them all to one side and then collect terms. I am just showing that I can pull this divergence out. The first term looks like curl of H, second is J, third is del D del T. Now, of course, this is not quite correct, because you know that I can always add any curl and this equation would still hold. So, I could not only add del D del T, but I could add plus curl of anything. up to this I can have, because when I take the divergence the curl will vanish and I do not know what this thing is, but I do know that I do need del d del t here, because I need to cancel out the divergence term that comes out of taking the divergence of j. So, this is where we had it. Maxwell reached this point. He said curl of H is equal to j plus del d del t, and of course, this is not unique. You can always add a curl to this equation. And at that point, he did not choose to add anything. He said, let us suppose we do not add anything, let us see what we get. So, this additional term he had was required just to conserve charge, and it is also motivated here, because we can see that just when curl of B fails to be 0, your electric field is time varying everywhere. So, you can surely expect to see that the electric field starts talking to the magnetic field. The working out of the details becomes very messy, and it is not necessary also, but the idea is that the moment you have a dipole, time dependent dipole forming, you have a dE dt, at the same time your curl of B is non-zero. So, this is the equation Maxwell came up with, and with that he came up with 4 equations altogether, which he said were complete in themselves. These equations were divergence of D is equal to rho, curl of E is equal to minus del B del T, divergence of B is equal to 0, curl of H is equal to J plus del D del T. So, you can see what has changed since we left electrostatics. First, we were forced to use this term in order to explain Coulomb's law for moving systems, and secondly, we were forced to add this term because you need to have charge conservation. Both of these have been forced on us. I mean, it is not as if they were required by observation. They are just forced on us by the fact that our equations are not suitable for time dependent systems. Now, this system of equations, these are what are called Maxwell's equations, are very powerful, and we will spend the next few lectures looking at just what they are saying. But I want to go back to something I said last time in order to emphasize why these equations are important. If you remember, when I was trying to talk about magnetic energy, I had this integral 0 to capital T volume integral over all space of, and I had a term which was divergence of E cross H, and there was another term which was H dot del B del T. Now, signs I do not remember which was which way, dV dt. And in discussing this issue of magnetic energy, I dropped this term. I said this goes to 0. The argument by which I went to 0 here was, I said electric field, if charges are far away, goes like 1 over r squared. Magnetic field, if currents are far away, goes like 1 over r squared. So, if I take this and I apply Gauss's law to it, I would get surface integral over a surface E cross H dot ds, which is something like 1 over r squared times 1 over r squared integrated over a surface which is 4 pi r squared. That is the area of a surface. So, it will go like 4 pi over r squared, which goes to 0. As I make the surface larger and larger, the importance of this term would become smaller and smaller. And this is why we dropped this term, and this is why we were able to get an expression for magnetic energy which said B squared over 2 mu. But there is something wrong with this statement. As it stands, it is correct, but once you add in this extra term del d del t, it turns out E does not go as 1 over r squared, H does not go as 1 over r squared, and in fact the surface integral of E cross H dot ds does not go to 0. And this is the remarkable thing that this equation has done. Just adding one term has completely changed the character of all the equations. And the importance again of this statement is that this one term, once you added it, was able to combine electricity, magnetism and optics. Now think about what optics is saying. Optics is saying that you have for example a star. Our sun is somewhere, it is 150 million kilometers from us, and the sun, we are told, is shining in all directions, and we are 150 million kilometers away. We get whatever little bit of radiation happens to fall on the earth, and we know that the amount of light that is falling on the earth, amount of radiation, is proportional to 1 over 150 into 10 to the 6 kilometer squared of the sun's total radiation. We know this is true because we know this is part of optics. We know in optics the light weakens as 1 over r squared, radiation weakens as 1 over r squared. So, the question immediately comes up is, what can light possibly do with electricity and magnetism? In electricity and magnetism, the energy stored in the field, which goes like E squared or B squared, will go as 1 over r to the power of 4, whereas here we are saying amount of radiation goes as 1 over r squared. So, there is something very different between electromagnetism of optics, or the theory of optics, and the theory of electricity and magnetism, which is why until Maxwell came, nobody connected the two up. To them they were two separate fields. Newton studied light, Huygens studied light, and Faraday, Maxwell studied electricity and magnetism. But when he added this one term, suddenly Maxwell obtained some new effects, and he found the theory of radiation was nothing more than a special case of electricity and magnetism. And this is a very profound thing. It suddenly simplified an entire field of physics. Optics just became a special case, and because of that we were able to generalize optics. We were able to say maybe there is an optics that works at larger wavelengths. Maybe the wavelength of light does not have to be a millionth of a meter, maybe wavelength of light could be 1 meter. If the wavelength of light were 1 meter, what would its frequency be? And that is where radio waves came from. The theory of radio waves came because Maxwell recognized that the theory of optics was nothing more than a special application of electricity and magnetism, and the moment you realize that, you can start changing the variables. It is all right, our eyes can see in optics, but maybe there are other rays also, and when you solve these equations you find in fact there are other rays, and when you look at what those other rays are, you find infrared waves, you find ultraviolet rays, you find X-rays, and of course you find microwaves, radio waves and other longer length waves. So, this particular generalization that Maxwell did, he just added one term, but it is far more than adding one term. People have been adding terms to these equations. The thing he did was he unified a whole set of different observations and gave a single theory that explained all of them. And that is why today we do not talk about this as Faraday's law and this as Ampere's law and different laws, they are just Maxwell's equations, because he was the one who made sense out of it all. The rest of them were giving individual laws. He said they are not individual laws, it explains something which is interconnected. We will come back to this, because this is explaining the inverse square law of radiation has to be the final goal of any electricity and magnetism course. Once you know that, then you can believe that electricity and magnetism can explain all of light. Okay. Now, there was one more way of looking at Ampere's law, and that was to say, supposing I have a wire and the wire is carrying a current. Now, I can draw a loop around that wire and I can do loop integral h dot dl. If I do loop integral h dot dl, I know that this is equal to surface integral over this connecting that loop curl of h dot ds, which is equal to surface integral j dot ds, which is equal to I enclosed. We have done this a dozen times now, and therefore, loop integral of h dot dl ought to be giving me the same answer. But you can make a thought experiment. You can say, supposing I break this wire at one point and I put a disc two discs which are separated by a dielectric, very thin dielectric. The discs have an area A and the dielectric has a thickness delta or d. So, I know that the capacitance of this disc is going to be epsilon A over d, where epsilon is the dielectric constant. However, the dielectric is a insulator, there is no current flowing in the dielectric. So, now I have this loop, drawing it dark just to emphasize. Now, I can connect this loop by a surface that intersects the wire. That is how I got I enclosed. But I could take the same loop, I do not move the loop, but I could connect it by a surface that did not cut the wire at all, that sliced through the dielectric. What does that mean? It means that this loop integral is still equal to surface integral. Let me call this surface S2. So, I will call this S2 curl of H ds, that is still true. It is equal to integral S2 of j dot ds, that is what Ampere's law says, is equal to I enclosed, but there is no current enclosed, because on that surface there is no current flowing at all. There is no current flowing here because it is air. There is no current flowing where the surface goes through the dielectric, because dielectric is a non-conductor. So, it is equal to 0. So, I have got two separate answers. In one case I have got the answer loop integral H dot dl is equal to I enclosed, which is I. In the other case I have got loop integral H dot dl is equal to 0. But it is one or the other. I have a current flowing and the current is not 0. So, loop integral H dot dl cannot simultaneously be 0 and I. It must be one or the other, or there must be something wrong with the equation. Well, this is Stokes' law, nothing can be wrong here, it is just a vector identity. This is definition. If I integrate the surface of over a surface j dot ds, it is the current going through the surface, so there is no problem. So, the only place where there can be a problem is here. Is it true that curl of H is equal to j? Well, we already know the answer. This is a third different way of looking at it. Curl of H is not equal to j. Supposing I add a del d del t, dot ds. Well, in the place where it intersects the wire, the electric field is very small, because we know that copper is a good conductor. So, there is hardly any electric field. This term is 0, whereas this term is large. Now, when I go through the capacitor, my electric field E is equal to the voltage divided by D in the direction from the plus plate to the minus plate, and the voltage V is equal to Q over C divided by D, because charge content is CV. And what is Q? Q is nothing but I times T divided by C divided by D. Now, this is the electric field. Let me put in the expression for C. So, what do I get? I get that the electric field is equal to I T divided by epsilon A. If I want to work with D, I have to use epsilon E, and the epsilon goes away. So, it is I T over A. Now, I want the derivative in time of D. So, this becomes, in this, when it is intersecting the dielectric, there is no current. So, this surface term goes away, surface integral S2 of I over A dot ds or dA. Now, this expression I over A is only correct over the region of the disk. Away from the disk there is no field, so I can remove it is 0. So, it is S disk, but the area of that surface is A. So, it is equal to I over A times A is equal to I. So, after all I get back Ampere's law. I got Ampere's law by using a simple surface, by the fact that it intersected the wire, and I got j dot ds over that surface was equal to I. and if I took a surface that went through the dielectric, J dot ds was 0, but this del d del t term gives me the same number, gives me I again. Now, this is why I did not do those complicated vector calculations, because I think I can convince you of the answer more easily directly. So, for these three reasons, firstly, if I take the basic building block of Biot-Savart, I find that curl of B is not 0 in the way Ampere's law requires it, and I recognize in Biot-Savart that I am having a time evolving dipole, electric dipole. So, there is a dE dt present, and when dE dt is present, my curl of B was not 0. Secondly, we looked at charge conservation. When we looked at charge conservation, we managed to get that we need a term that looks like del d del t. And thirdly, when we tried to do curl of H and compute its value by two different means, we find that in one case you get I due to the conduction current, in the other case you get the current I due to what is called the displacement current. This del d del t is called it's only a name. Ultimately, it is required because the time changing electric field induces magnetic field, even as the time changing magnetic field induces electric field. So, both of these are happening. You have an electric field caused by time rate of change of magnetic field, you have a magnetic field caused by time rate of change of electric field. Now, I want to end the lecture today by putting all these pieces together and showing you that they give you something entirely new. So, what I am going to do is I am going to assume that I have an electric field in the x direction and a magnetic field in the y direction, and this electric field E is in the x direction, and I am going to assume it has some dependence on z and t. So, the electric field does not change in the direction x, but it can change in the direction z. I am going to assume the magnetic field B is some B naught in the y direction and is some other function g of z t. And then I am going to try and apply the various Maxwell's laws and see what comes of having such fields. So, if I take divergence of B, the direction of B is y, so it is equal to del del y of B naught times some function g of z t, which is equal to 0, because g is a function of z and I am taking the derivative with respect to y. If I take the divergence of D, which is epsilon E, I get epsilon naught E naught times del del x of f of z t, which is again 0, because f is not a function of x, f is only a function of z and t. I will further assume that there is no rho and there is no j. Now, if I want curl of E, I clearly need something that can differentiate E, and the only spatial direction in which E is varying is z. So, it must be del del z of the electric field along x E naught f of z t. So, if I have something whose derivative is z acting on the x component, it must be in the y direction. And this we are told is equal to minus the magnetic field. Well, luckily the magnetic field is in the y direction, it is B naught g of z t. So, that gives me an equation, because both are in the same direction. So, I can write down this equation. The equation I get says del del z E naught outside of f of z t is equal to minus B naught g of z t. Sorry, this should be del del t of, because it is minus the time rate of change. Del g del t. Now, if I apply the same thing to B, I need curl of B is equal to, well, B is in the y direction and it depends on z. So, I must take the z derivative, del del z of B naught comes outside g of z t. Now, if I have the z derivative of something along y, it must be along the x direction. So, it is in the minus x direction, because if you look at the standard term for curl along x, it will be x hat del del y of B z minus del del z of B y. So, I do not have a B z, I have only a B y. So, there is a minus sign. So, that minus sign comes. This curl of B is equal to mu naught j, but there is no j, and it is also equal to mu naught del d del t. D is nothing but epsilon E. So, it is mu naught epsilon naught times del del t of electric field, E naught del f del t. So, let us write down that equation as well. It says that again the x direct, both are in the x direction. So, I have an equation now which says minus B naught del del z of g of z t is equal to mu naught epsilon naught E naught del f del t. So, I have two equations with which I can try and solve the system. But this involves g and this equation for g involves f. So, I need to eliminate g. If I do not eliminate g, I will not get an equation for one variable. I require del g del z and I have del g del t. So, I will take another derivative with respect to z. So, I will take E naught del squared del z squared of f is equal to minus B naught del del z of del g del t. Now, as you know, second partial derivatives can interchange. So, I can write this as minus B naught del del t of del g del z, and now I can use this because I have B naught del g del z right here. So, it becomes mu naught epsilon naught E naught del squared f del t square. This E naught is common, so I can remove it from the equation, and I get the final equation, which is del squared f del z squared is equal to mu naught epsilon naught del squared f del t square. This equation is the equation Maxwell derived, and this is the equation that suddenly changed everything, because mu naught epsilon naught, when you work out the numbers, is nothing but 1 over the square of the speed of light in vacuum. Now, it is not an accident. In fact, I would say mu naught and epsilon naught are deliberately obscure constants. If you used a different system of units, this equation would naturally have had 1 over c squared in it. Mu naught and epsilon naught were derived more for convenience of use and not for convenience of thinking. But what is more important is, if you look at this equation, I will derive it next time, you will find that there are solutions f is equal to some function of z minus ct plus some other function, not the same function. So, I will put a twiddle of z plus ct. So, when you look at this, you find that this system supports solutions which move without decaying. They can go to the end of the universe without obeying the inverse square law of Coulomb's law. I can have a source that generates this disturbance and it will go far away without losing its energy. We will do the rest of the derivation next time when we complete the wave equation.